Find the discontinuities and classify them as removable or non-removable. Also, identify all vertical and horizontal asymptotes. In this first function here, this is just a straight out rational function. You need to factor the numerator and denominator to get this. F of x equals x times x plus 3 times x minus 1 all over x times x minus 1 squared. And here we can start noting what discontinuities you have. You have a discontinuity at x equals 0 and at x equals 1. So f of x is discontinuous at x equals 0 and x equals 1. So now we can start classifying these things by whether or not we cancel and see what is left. So we can cancel an x in the numerator and denominator, and we can also cancel an x minus 1 in the numerator with an x minus 1 in the denominator. And that leaves you with a function of f of x equals x plus 3 over x minus 1. So you may have learned before that when you cancel a factor, that leaves you with a hole in the graph. Well, we canceled an x, and that's a hole in the graph, which makes x equals 0 a removable discontinuity. And you also see that we canceled an x minus 1 in the numerator and denominator. But down here in the denominator, there's still a factor of x minus 1. So even though we factored out and canceled an x minus 1, there's still one left in the denominator. That makes this x equals 1 a vertical asymptote. And vertical asymptotes are non-removable. So we have all of the vertical asymptotes now of this graph. We just need the horizontal asymptote for this graph. And since the numerator and denominator have the same degree, we can use the ratio of the leading coefficients. So down here underneath the vertical asymptote, the horizontal asymptote is y equals 1. In this next example, we have f of x equals 1 over x if x is less than or equal to negative 1, or 2x plus 1 if x is greater than or equal to negative 1. So what needs to happen when you have a piecewise function is you need to check each function for discontinuities on the interval, and then you need to check where the domain breaks to see if it's continuous at that particular x value, in this case, negative 1. So we start with the first function. We have 1 over x. 1 over x exists on the domain negative infinity to negative 1. So when you find the discontinuities of this particular function, you know that there's a vertical asymptote at x equals 0. Well, this is not in the interval, so this discontinuity does not come into play. When you look at the second function, so the first function is continuous on its interval, from negative infinity to negative 1. The second function is 2x plus 1 on the interval including negative 1 to infinity. And since 2x plus 1 is linear, it's continuous. So the only place that this graph or this function might not be continuous is when x equals negative 1. So down here, in order to prove that, we know that in order to be continuous at a point, that the left and right limits have to be equal, and the function needs to be defined at the same value you get for those two limits. So let's take a look at that. If you look at the limit as x approaches -1 from the left of f of x, that is the same thing as writing the limit as x approaches -1 from the left of this portion, because that is less than -1. So the limit will look like this, which allows us to substitute that -1 right in for x and get back a value of -1. The next limit we need to check is the limit as x approaches -1 from the right of f of x, and that looks like this. And again, we can substitute this -1 right in for x and get -1 for an answer. So we have a left and right limit equaling -1. If you will recall that a limit can still exist if there's a hole in a graph. So the last thing we need to check is that the limit as x approaches -1 of f of x is the same thing as f of -1. When you check this out, you can look right here in this limit that the -1 was directly substituted into that function. So f of -1 up here in the original function is what you get when you substitute -1 into that same part of the function. So we know that these two things are equal. So f of x, our conclusion, I'm going to write that in blue, right down here, is that f of x is continuous everywhere. On this page, we will be following the exact same directions to look at these two functions. We're trying to find all discontinuities and classify them, also finding all vertical and horizontal asymptotes. So in this first example on the left, we have two functions here. We have 2 over x plus 3 if x is less than -1, and x squared minus 2x if x is greater than or equal to -1. So we have to check each function individually to see whether or not there are discontinuities there. So 2 over x plus 3 is discontinuous at x equals -3. There's a vertical asymptote there. And even better is that x equals -3 is on the interval -infinity to -1, which is the exact same way of writing this domain here. So this is a vertical asymptote on the given domain for that function, which means it is non-removable. So we have a non-removable discontinuity at x equals 3, for sure. And it's also a vertical asymptote. For this other function, x squared minus 2x is continuous everywhere. So if it's continuous everywhere, it will also be continuous on a restricted domain. So that's not a big deal. What we need to do now is see if the function k of x is continuous at -1. So what we do is we check the limits again. The limit as x approaches -1 from the left of f of x is the same thing as writing this limit, because from the left means less than, which function is less than -1 here. So when you substitute the -1 directly into x, which you're allowed to do, you'll get -1 back in return. So now we need to check the limit as x approaches -1 from the right of f of x, which is the following limit. And if you directly substitute -1 in here for x and here for x, you'll get back a +3. So since these two limits do not match, there is a non-removable discontinuity at x equals -1. It's not a vertical asymptote, it's just that these two functions don't meet up at a single y value. So we found a non-removable discontinuity and a vertical asymptote at the same time at x equals -3. We found a non-removable discontinuity here at x equals -1. What else did we need to find? Horizontal asymptotes. There's one horizontal asymptote up here in this first function. So there's a horizontal asymptote at y equals 0. In the other function, f of x equals the tangent of pi over 2x, let the trig loose. Normally, the tangent function has a period of pi. However, the new function, or the new period, is always pi over absolute value of b. And b is whatever is being multiplied to the x. So the new period will look something like this. It'll be pi over 2. And when you, flip and multiply, you'll get an answer of 2. The new period is 2 wide. Also, with a tangent function, there is a vertical asymptote halfway through each period. So given that information and some sort of number line here, we'll start it at 0. We'll go to 2, we'll go to 4, we'll go to -2, we'll go to -4. So I'm going to mark over here in red. Halfway between 0 and 2 is 1. Halfway between 2 and 4 is 3. Halfway between 0 and -2 is -1. Halfway between -4 and -2 is -3. So all of these red dashes are where vertical asymptotes happen. So it looks like every odd number, which can be represented in the following way. We can say there are vertical asymptotes at x equals 2k plus 1, where k is an integer. So that's it. We have a vertical asymptote at every odd number. And vertical asymptotes are non-removable discontinuities. So there are an infinite number of discontinuities in this tangent function.